Imagine trying to build a machine thinner than a human hair directly on the surface of a lake. This isn't science fiction. In a groundbreaking leap for robotics, scientists are now weaving functional robots directly on water. This new technique, called Hydro-Fabrication, is allowing us to create tiny water-walking machines that could one day swarm across our oceans to monitor pollution or skim across floodwaters in search of survivors. We're moving away from the clunky, rigid robots of the factory floor and into a new era of machines that are soft, adaptable, and born from the very environment they're designed to explore. For decades, the word robot meant something made of hard metal and plastic. Think of the giant, powerful arms in a car factory. They are incredibly strong and precise, but that very rigidity is also their biggest weakness. Put one of those robots in an unpredictable environment, like your home, or ask it to handle something delicate, like a piece of fruit, and its strength becomes a liability. The materials are just too stiff, billions of times stiffer than living tissue, making them clumsy and potentially dangerous for direct interaction. This limitation gave rise to an entirely new field, soft robotics. Instead of fighting against complexity and softness, these engineers decided to embrace it. They looked to nature for inspiration. Think of an octopus, with no bones at all, using its arms with infinite flexibility. Or a humble earthworm inching its way through soil. These creatures are masters of movement, without a rigid skeleton. Soft robotics aims to copy these biological miracles, creating machines from highly compliant materials like silicones, gels, and fabrics. In soft robotics, the material is the machine. The robot's ability to move and function comes from the inherent properties of the materials it's made from. A soft gripper, for example, can wrap around an object of any shape with a single puff of air, a task that would require a complex array of sensors and motors in a rigid robotic hand. Instead of traditional motors and gears, these robots often use ingenious methods like pneumatic networks, where pressurized air inflates channels inside the soft body, causing it to bend and move. A key early inspiration for this was the McKibben artificial muscle, invented way back in the 1950s. It's a simple tube inside a braided mesh that contracts when you inflate it, much like a real muscle. But the field truly blossomed in the 21st century. A huge milestone came in 2016 with the Octobot from Harvard University. It was the world's first completely soft and autonomous robot. It had no rigid batteries or circuit boards. It moved using a chemical reaction that generated gas to power its tiny pneumatic tentacles. Then, in 2021, a soft robot inspired by the snailfish successfully swam in the Mariana Trench, the deepest part of the ocean, proving these machines could conquer even the most extreme environments. So how do you actually build one of these squishy machines? Traditionally, the most common method is molding and casting. You design a negative mold, often with a 3D printer. Pour in a liquid silicone, let it cure, and then piece together the different parts. It's versatile, but it's a slow, multi-step process. Bonding different layers together can also create weak spots where the robot might fail. More recently, 3D printing has been a game changer, allowing for incredibly complex designs to be printed in a single piece. Techniques like direct ink writing can extrude a variety of soft materials, like silicones and hydrogels, almost like a high-tech piping bag. But even with 3D printing, there are challenges. It's hard to print with the super soft materials you really want, and the process can be slow. And both of these methods run into a huge problem when you try to make something extremely thin and delicate. Imagine creating a functional film that's thinner than a human hair. The final step is peeling it off your solid workbench. The slightest mistake and the film tears, wrinkles, or folds onto itself. It's a frustrating bottleneck that has held back the creation of ultra-thin, aquatic soft robots. This is the exact problem that a new technique called HydroSpread, developed at the University of Virginia, elegantly solves. The core idea is brilliantly simple. If moving the delicate film from the workbench is the problem, then get rid of the workbench. Use water instead. The process starts by dropping a tiny bit of liquid polymer onto a bath of water. Thanks to surface tension, that droplet spontaneously and evenly spreads out, forming an impossibly thin film, as thin as 100 micrometers. Once the film is spread, it's cured with UV light, turning it from a liquid into a solid, flexible sheet that's just floating there. Now for the truly revolutionary part. Instead of trying to move that fragile film, a precisely controlled laser is used to cut and pattern it directly on the water's surface. This is where the magic happens. Water is a massive heat sink. As the laser cuts, the water underneath instantly whisks away all the excess heat. This prevents the melting, warping, and rough edges that you'd normally get when laser cutting thin polymers on a solid surface. The result is incredibly precise, clean cuts, allowing engineers to carve complex, functional shapes directly onto the floating film. By building the device right on the water, the entire perilous transfer step is eliminated. But these aren't just passive floating shapes. They are designed to move. This is achieved by using what's called a bilayer film. The film is made of two distinct layers, and each layer has a different coefficient of thermal expansion. This just means that when you heat them, one layer expands more than the other. This mismatch in expansion forces the film to bend. By carefully designing the shape of the laser-cut film, researchers can program this bending into specific, useful movements. One of their prototypes, named HydroFlexor, has a central body and two wing-like fins. When it's heated from above by an infrared lamp, the fins perform a complex bending and twisting motion, paddling against the water and propelling the robot forward. Another prototype, the HydroBuckler, was directly inspired by the water strider insect. It has a central body with several thin, leg-like structures. These legs are engineered so that when they're heated, they don't just bend, they buckle. Buckling is a rapid, almost instantaneous change in shape. This sudden, forceful movement mimics a walking or jumping motion, pushing the device across the water's surface. By cycling the heat on and off, researchers can control the robot's speed and even steer it by selectively heating different parts. Now, this idea of using water as a key component in robotics isn't entirely limited to building things on water. There's another class of water-based materials called hydrogels. These are 3D networks of polymers that can absorb and hold huge amounts of water, sometimes up to 99% of their mass. This gives them a softness and biocompatibility that is incredibly similar to living tissue. Hydrogel robots are made of water, not just on water. They often move because they are designed to be stimuli responsive. This means the hydrogel network can swell or shrink in response to triggers in its environment, like changes in temperature, pH, or light. By embedding magnetic particles, you can even make them move with a magnetic field. Because they are so biocompatible, hydrogels are incredibly promising for medical applications. Imagine tiny hydrogel robots navigating your bloodstream to deliver drugs directly to a tumor, or soft hydrogel surgical tools that can manipulate delicate organs with almost no risk of damage. Researchers at MIT have even created tough, 3D printed hydrogel actuators that are powerful enough to grab and release a live fish without harming it. So we have two distinct approaches to